All right, happy Monday. The menu for today involves matrices, their inverses, and determinants. So these shouldn't be completely foreign words. So we've talked about inverses in methods, it being something that undoes. Okay, so what we're looking at today is to be able to undo matrix multiplication. So our goal by the end of the day is to be able to reverse multiplication. So we don't call it division because that's not exactly what it is. We will call it finding and multiplying by the inverse. Okay, so this inverse thing, okay, so it's in black because we've got a definition. So the inverse is an operation, so this is just in general, which, undoes, okay, another. Generally, we're talking about multiplication. Okay, just kind of a little sub-meaning. For any value A, the inverse is denoted. Okay, so denoted means written as. Put a little equation in here. Okay, A to the negative 1. Okay, so whether it's a matrix or a number, okay, we denote the inverse as to the negative 1. Okay. Also important that the inverse has the property that the product of A and the inverse is the identity. Okay, so in just real numbers, our identity is 1. Okay, whereas in matrix multiplication, we talked about this on Thursday, it's got the diagonals as zeros or as ones, sorry, and zeros everywhere else. So what happens if I do A times A inverse? Well, I get I, where I is the identity. Okay, so inverse, it's an operation which undoes another. That's just generally speaking. If I have some value A, we denote it as A to the negative 1. And we have this property that when I multiply the original value by its inverse, I get out the identity. Again, because we're particularly talking about matrices here, it will be the identity matrix. Okay. So one second. All right, so our big goal for today. So by the end of today, we want to find a matrix. It's got this special name, A inverse. I'd really prefer, again, like if you don't say A negative 1, it's A inverse, okay? Such that A times A inverse, is equal to the identity, and multiplication, again, should work both ways, so 2 times 3, 3 times 2. Also, we want that A inverse times A is equal to the identity. Again, we do really need to specify when we're working with matrices that it will work whether we multiply the A inverse on the front or the back, because we've seen many times that the product of two matrices is not the same whether it's AB or BA. In particular, it can even be a completely different size. The fact that we can multiply A and A inverse and A inverse and A requires that their orders be the same, okay? In particular, that their orders are square. So just a little note, this means that both A and A inverse, okay, must be square. Okay, so we will only be finding the inverses of square matrices. The inverses of other matrices simply do not exist. Okay, so you just can't find any matrix anywhere that has this property. So we've got another definition for today, and it is the determinant. It's a very important sounding word. What the determinant is, it's this value for every matrix, okay, which tells us whether we can invert it or not. So does it have an inverse? I'll talk about how we can determine that in just a second, but it is a value for every matrix which defines, I'm going to say, the invertibility. So whether you can find the inverse or not. We can use the CAS to find it. Okay, so there's a little function. If I give you a matrix, it will give you the determinant. Okay. We can find it by hand for 2 by 2. You can find it by hand for 3 by 3, 4 by 4, but it can be a really long process, so we'll only do it by hand for 2 by 2s. We use the notation det of A, okay, determinant of A, or basically the absolute value of A, or our little symbol, which is a little triangle. Okay, so this symbol might look familiar. We called it the determinant, and it told us how many zeros a quadratic had. Same idea, it tells us a factor about it. Okay, so we've got this inverse. Not all matrices have an inverse. If they do, we use the determinant to check. Okay. So, just going to switch the font back to red because this is very important. Only matrices with non-zero determinants have inverses. Okay, so what do I mean by that? If you find the determinant, again, we'll talk about how to find it in just a second, but once you find it, if it's 0, it means there's no inverse. Only matrices with non-zero determinants actually even have these inverses. So there's no point in doing all this work to find the inverse if it's not actually going to exist once you get to doing the calculation. So what we have is, okay, so on the CAS, so as I mentioned, the CAS can find it for any size of matrix. And it's as simple as typing det of A, and that will tell you its determinant. Again, it will be a single number value. We're just checking, is that number 0 or not? By hand, a little bit more involved. Just write it out manually here. So for A, which is some teeny tiny 2 by 2, going across the first row AB, across the second row CD, the determinant of A is going to be the product of A and D minus the product of B and C. So AD minus BC. So if you're doing it for just a 2 by 2, often you can just look at it and calculate that in your head. It's going to be quicker to do it by hand than on the CAS, whereas if it's a 3 by 3, by default you will have to go to the CAS. Alright, so let's do a few examples of finding this fun little determinant thing. So I've got 3 matrices here, all of them 2 by 2, so we can do them all by hand. Okay, so our first one is A. We want to determine find the determinant of each matrix and state if it is invertible or not. So can we even find the inverse? So the first one is A. It is 1, 2, 3, 4, my favorite little simple matrix. So here, if we're looking to find the determinant, my determinant of A, okay, is AD minus BC. So it's the diagonal going from top left down and then top right down. Okay. Now this is going to be equal. So AD, that's 4 times 1 minus BC, which will be 2 times 3. That becomes 4 minus 6, or negative 2. So looking at this, we see that our determinant is negative 2. Negative 2 is most definitely not 0, so this thing will have an inverse. Okay, so with this example, it is important to actually answer the questions. We have found the determinant, that's step 1. Step 2 is to state if it is invertible or not. So I'm going to say, well, negative 2, that is not equal to 0, so there is an inverse. Just get that down on the next line. So it is important to make your final conclusion. Our next matrix up on the lineup is B, which is negative 1, 2, negative 3, 6. So again, our equation for determinant is AD minus BC, so that one diagonal minus the other of their products. Okay, so this becomes AD, that's 6 times negative 1. And I've written them in that order so that I can put the negative 1 in brackets, minus 2 times negative 3. Okay, simplifying this, we get negative 6 minus negative 6, which is negative 6 plus 6, or 0. Make that pretty. Okay. Since det of B is 0, there is no inverse. Okay. Got no inverse happening on that one. Now with C, let's have a look. Again, our formula, AD minus BC, so the one diagonal minus the other. Filling that in, AD, that's 5 times 7, minus negative 5 times 7, or 35 minus negative is plus 35, or 70. So my point with this one is just be very careful with your signs. 70, again, most definitely not equal to 0, so there is an inverse. So first of all, we do generally want to know if there is an inverse at all. Now that we know for A and C there are indeed inverses, let's figure out how to find out what they are. Alright, and now for the part that you've all been waiting for, how do we find this inverse thing? So, as I said, can be done by hand for a 2x2 and is almost quicker to do by hand than on the CAS, but if we're looking at 3x3, 4x4, most definitely we are going to use the CAS. So for now, just looking at 2x2 matrices, again, generally just so I can talk about locations, I'm going to call the matrix A with values A, B, C, and D. Again, it's just easier than labeling the locations. So how do we define this inverse? Well, first of all, it has a coefficient of 1 over the determinant of A. This explains a little bit why the determinant can't be 0, because if I was to apply the little formula, I would be dividing by 0, and that is a big no-no. So because we've got this determinant as the denominator of a fraction, that's pretty much the reason why it cannot be 0. That's why the inverse would not exist. Now what we do to the actual matrix component is we swap A and D, so they switch locations, and we change the sign of B and C. So if it was negative, it becomes positive, and vice versa. We can simplify this a little bit by putting in the calculation for the determinant. So it's 1 over AD minus BC times matrix A, but swapping A and D and changing the sign of B and C. On the CAS, you literally type A to the -1 once you've defined your matrix, or you can bring the power on the matrix itself. So let's do a couple of examples here. So I'll give you the matrix and I'd like you to find the inverse. All right, so here we go. If it exists, find the inverse of each matrix by hand. So we've got 3 there. Some will work, some will not. So we're starting with A, which is the same matrix we looked at in part A previously. So we can just start plugging away. As soon as we get to that step where we divide by the determinant, it'll be very clear whether it exists or not. So we can just start the calculation. If we start dividing by 0, we can stop. This one we do know has an inverse because we did this one earlier. So A inverse is 1 over, 1 times 4 is 4, minus 2 times 3 is 6, times, it's close to A, but we're going to swap A and D. So where there was a 4, there's a 1, and where there was a 1, there's a 4, and I changed the signs of the other two. Okay. So we simplify that. So 1 over 4 minus 6, that would be a -1/2 times this matrix here. And then you can choose to leave it out front as a coefficient, but I'm going to actually multiply it in. Okay. So if we actually take these values and multiply them by -1/2, okay, half of 4 is 2, but it will be negative. Half of 2 is 1, but we're changing the sign, so it will now be positive. -3 times -1/2 will be positive 3/2, and then -1/2 times -1 will give me -1/2. And that matrix there, -2, 1, positive 3/2, and -1/2 will have this lovely property that when I multiply it by A, it will give me the identity. So we start off on B, same way. B inverse, well, that would be defined as 1 over 2 times 12, which is 24, minus 24. Okay. Pretty much there you can stop, because you'll recognize that denominator, 24 minus 24, is most definitely 0. So stop. Det of B is 0, so no inverse. Okay. Again, if you start the process, you will see that no inverse exists. Okay. Now finishing up with part C, I'll give you a minute to try it on your own. So pause when you're ready, try it on your own. Okay, now we're looking at C, inverse. Okay, starting with the coefficient outside, 1 over 2 times 5 is 10, minus 3 times 3 is 9. Ooh, I must have picked a nice one for you. Times, okay, just so I don't have to format the matrix again. The A and the D swap places, and the B and the C become negative. Now, this one, okay, I specifically chose just for you because it works out quite nicely. Hopefully we can all recognize that 10 minus 9 is 1, so the coefficient is just 1, meaning this matrix right here is our final answer. Okay, so the inverse of 2, 3, 3, 5 is 5, -3, -3, 2. Okay, Now, as of right now, you're basically trusting me that this works, so let's confirm with part C that when I multiply on both sides with the inverse, that it does become the identity. All right, so let's indeed show that this was the inverse by doing a little bit of matrix multiplication. So example 3, show that C inverse from example 2 is indeed the inverse by showing that C times C inverse is the identity and that C inverse times C is the identity. Now, this is a little bit of practice with matrix multiplication that we were doing the other day, so I'll give you a moment to try it on your own. All right, so here we have set up C times C inverse. So doing a little refresher of our process. We go row by row and column by column, multiplying each pair together. So our first pair in location 1, 1 will be 2 times 5 plus 3 times negative 3. Okay. You can choose to do the calculation in your head or enter it yourself. Okay, our next pair would be 2, 3 and negative 3, 2. Okay, going through each of the pairs. 3, 5, 5, negative 3, and last but not least, the bottom and last pair. Now we'll do a little reveal here. Okay, so what we do find is that when we multiply row 1 by column 1, that's 2 times 5 or 10, minus 9. When we go to the next, 2 times 3, negative 3, 2, we get negative 6 plus 6, and so forth. You might be doing the addition in your head right now, but you most certainly would find that in the end we do get the identity. So that 2 times 5 gives us the 10, 3 times negative 3 gives us the negative 9, and they have a sum of 1. 2 times negative 3 is the negative 6, 3 times 2 is the positive 6, together giving us 0. Okay, 3 and 5 give us the 15, 5, negative 3, the negative, and then negative 3 times 3 is negative 9, and 5 times 2 is 10. Their sum is 1. So that side checks out. But in order to be the inverse, it needs to work on both sides. So I must be able to multiply either way. All right, and a little bit of magic has happened. We've done C inverse times C, and story checks out. The inverse did work. So again, where these numbers come from. Okay, first row times first column. 5 times 2 is 10. Negative 3 times 3 is negative 9. Then we move on to the next a little bit, which is first row times second column. 5 times 3 is 15. Negative 3 times 5 is negative 15. And then we keep going. Negative 3 times 2 is negative 6. 2 times 3 is positive 6. Negative 3 times 3 is negative 9. 2 times 5 is positive 10. Again, giving us the good old identity matrix. So check. This process does indeed work. So now you'll have a good chance to practice working through some of the questions in 3.3.